Hello friends, welcome to my lecture on predicates and quantifiers. There will be 2 lectures on this topic. This is first lecture on this topic. We have so far discussed the simple statements and the logical techniques to combine simple statements into compound statements. Now, these techniques cannot be applied, we cannot apply these techniques to convert the following sentence into a mathematical statement just by using propositional logic. Every person who is 18 years or older is eligible to vote. The problem here is that the propositional logic is not enough to deal with quantified variables. It would have been easier if the statement were referring to a specific person. Therefore, we need a more powerful type of logic. We discuss now predicate logic. It is an extension of propositional logic. It adds the concepts of predicates and quantifiers to express statements that cannot be adequately expressed by propositional logic. Now, let us see what is a predicate. Let us consider the statement x is greater than 3. This statement has 2 parts. The first part is the variable x, which is called the subject of the statement. The second part is greater than 3 is the predicate. Thus, a predicate refers to the property that the subject of the statement can have. The statement x is greater than 3 can be denoted by p x, where p denotes the predicate is greater than 3 and x is the variable. The predicate p can be considered as a function. It tells the truth value of the statement p x at x. Once a value is assigned to the variable x, the statement becomes the statement p x becomes a proposition and has a truth value denoted by t or a false value denoted by f. P x in general, a statement involving n variables x 1, x 2, x n can be denoted by p x 1, x 2 and so on. Here p is referred to as nth n place predicate or an n-ary predicate. Let us look at the example 1. In example 1, let p x denote the statement x greater than 10. Then the truth value of p 11 and p 5 are t and f respectively, because p 11 is equivalent to the statement 11 greater than 10, which is true, while p 5 is equivalent to the statement 5 is greater than 10, which is false. In example 2, let r x y denote the statement x equal to y plus 1, then the truth values of the propositions r 1 3 and r 2 1 are f and t respectively, because r 1 3 will denote 1 equal to r 1 3 denotes the statement denote the proposition 1 equal to 3 plus 1, which is false. While r 2 1 denotes the proposition 2 equal to 1 plus 1, which is true. So, the value of the proposition r 1 3 is f, and the value of r 2 1, the proposition r 2 1 is t. The expressions of the type p x are called propositional functions or open sentences. Let A be a given set. An expression denoted by p x is called a propositional function or open sentence or a predicate on A if p a is true or false for each a belonging to A. That is, p a has a truth value for each a belonging to A. In other words, p x is called a propositional function or an open sentence on A if p x becomes a statement whenever any element A belongs to A is substituted for the variable x. Let p x be, for example, let p x be x plus 6 less than 9. Okay? Then p x is a propositional function on the set of all natural numbers. Let us see that how it is a propositional function. When you take the natural number 1, then p 1 is equal to 1 plus 6 less than 9, which is not true, but sorry, which is true. Okay. So, the value of P 1 is t here, P 2 is 2 plus 6 less than 9, which is again true. The value is t. 3 plus 6 less than 9 is not true, 9 less than 9 is not true. So, we have the value false here. 3 plus 6 is 9, 9 less than 9 is not true. So, the value is false here, and P 4 plus 6 less than 9 okay, is again untrue. Okay. So, the value is false here, and P 5 P 6 okay, they are all false, because 5 plus 6 is less than 9 okay, is not true. Okay. Then 6 plus 6 less than 9 is also not true. So, P 5 P 6 they are all having truth value f. P 4 this is f, and P 3 is also f. Okay. So, the truth value of P 1 is t, the truth value of P 2 is t, the truth values of P 3, P 4, P 5, P 6 and so on, they are all f. Now, let us take another example. Let P x be x plus 3 less than 6. Okay. Then P x is a propositional function on the set of all natural numbers. Clearly, the statement P 1 P 2 are true. P 1 is 1 plus 3 less than 6, which is true. So, P 2 is 2 plus 3 less than 6, which is again true. Okay. Now, when x takes value 3, P 3 then 3 plus 3 less than 6 is false. So, we have the truth value of P 3 as f, and truth value of P 4 is also f, because 4 plus 3 less than 6 is false. Okay. So, the truth values of P 3, P 4, P 5 and so on, they are all f. Okay. Thus, P x has a truth value for each x belonging to n, and therefore, P x is a propositional function on the set of all natural numbers. Now, let us take another example. Let P x be x plus 3 less than 6. Okay. Again, we are taking P x to be the same inequality x plus 3 less than 6. Then P x is not a propositional function on the set of complex numbers C. Okay. Set of complex numbers is noted by C, because if you take x equal to say 2 I, okay, then 2 I belongs to C, but 2 I plus 3 less than 6 is not defined. Okay. So, since inequalities are not defined on C, okay, therefore, P x for a given x belonging to C does not have a truth value t or f, and therefore, P x is not a propositional function. Let us define a truth set. Let P x be a propositional function on a domain D, then the set of elements D belonging to D with the property that P D is true is called the truth set T P of P x. Okay. So, for all those D belonging to D for which P x has the truth value T, okay, we say that those elements form the set truth set of P. Okay. So, the truth set T P, we denote truth set by T P. Okay. So, T P is equal to set of all x such that x belonging to D and P x is true, or we can also denote it by T P equal to x such that P x. Okay. In short, we write T P equal to x such that P x. Now, example, let P x be x plus 2 less than 3, okay, and D is the set of all natural numbers. Then T P will be equal to set of all x belonging to n, x plus 2 less than 3. Now, you can see if x takes the value 1, okay, then 1 plus 2 less than 3 is not true. Okay. Similarly, when x takes values more than 1, that is 2, 3, 4 and so on, x plus 2 is not less than 3, therefore, T P is equal to 5, because x plus 2 less than 3 is not true for any x belonging to n. Now, let us take another example. Let P x be x greater than 2, okay, and D is the set 3, 4, 5 and so on. Then T P is equal to D, because for all x belonging to D, okay, the inequality x greater than 2 is true. Okay. So, T P is the whole of D. Okay. Let us now define quantifiers. To express the truth value of a predicate, okay, with respect to a set of objects, we use the quantifiers. Quantifiers refer to quantities such as some, all, none, some, all and none. Okay. Universal quantifier, consider the statement all human beings are mortal. Here the property being mortal refers to all human beings. The symbol, this symbol is used to denote the quantity all of objects for which a given predicate is true. Since this symbol represents a quantity, we call it a quantifier. Further, the quantity is all, okay. The quantity is all, the property is, that is, the property is true for all objects. Therefore, this symbol is called as universal quantifier. Let p x be a propositional function defined on the set D if for every x belonging to D, p x is a true statement. Then using universal quantifier, this universal quantifier, we write it as for all x belonging to D, p x, okay, or for all x, p x, or for all x comma p x. Okay. So, this means that this notation means for every x belonging to D, p x is true. Okay. Since the truth set of p x is the entire set D, okay, the truth set of p x, okay, the truth set of p x is the, because for every x belonging to D, p x is true. So, the truth set of p x will be entire set D and therefore, T p equal to D. Now, let us take the example, the statement for all n belonging to n, n plus 2 is greater than 1. You can see, take any n belonging to n, say n equal to 1, 2, 3 and so on, then n plus 2 is always greater than 1. Okay. Therefore, its truth set is the whole of n, T p is equal to 1, 2, 3 and so on, that is whole of n. The statement for all n belonging to n, n plus 1 greater than 5. Okay. This is false, because when n takes values 1, 2, 3, okay, 4, then n plus 1 greater than 5 is not true. Okay. So, the truth T p here is 5, 6, 7. Okay. When n takes values starting with 5, that is 5, 6, 7 and so on, then only n plus 1 greater than 5 is true. Okay. So, T p here is equal to 5, 6, 7, the set consisting of 5, 6, 7, which is not equal to n, and therefore, this statement is false. So, let p x denote the statement x plus 2 greater than 5. Okay. Let p x denote the sentence x plus 2 greater than 5, state whether or not p x is a propositional function on the following set, on each of the following sets. So, let us take first the case n. Okay. In the case n, you take any x belonging to n, okay, say x is equal to 1. Okay. Let us say let x be equal to 1, then 1 plus 2 greater than 5 is false, okay, not true. So, we have truth value f, x equal to 2. Okay. If we take then 2 plus 2 greater than 5 is again not true. So, the truth value is f, and then we take x equal to 3, then again 3 plus 2 greater than 5 is not true. Okay. So, truth value is 5, okay, but when x takes values 4, 5, 6 and so on, okay, then x plus 2 greater than 5 is always true. Okay. So, the truth value is t. So, for all x belonging to n, okay, the sentence p x given by x plus 2 greater than 5 has a truth value t or f, okay, and therefore, p x defines a propositional function on the set n. While now, let us take the other case m equal to minus 1, minus 2, minus 3 and so on. Okay. So, here if you take x to be say minus 1, then minus 1 plus 2, okay, is equal to 1, 1 greater than 5 is not true. When you take x equal to minus 2, 0 we get, x plus 2 is 0. So, 0 greater than 5 is not true. When you take x equal to minus 3, again we get minus 1 greater than 5, which is not true. So, for every x belonging to m, okay, any x belonging to m, okay, if you take, then x plus 2 greater than 5 is not true, that is truth value is f. and therefore, for every m x belonging to m, okay, the sentence x plus 2 greater than 5 has a truth value which is f, and therefore, p x defines a propositional function on m. Now, let us take the set of all complex numbers. If you take any x belonging to C, say x equal to, if you take 2i, okay, a complex number, a purely complex number, if you take x equal to 2i, then 2i plus 2 greater than 5 is not defined, because inequalities are not defined for complex numbers. Okay. So, we cannot decide about the truth value whether it is T or F, and therefore, P x does not define a propositional function on C. Let take the example, let R be the universal set, R is the set of all real numbers, okay. Then determine the truth value of each of the following statements. First statement, let us take for every x such that mod of x equal to x. Now, if you take x equal to, if we take x equal to minus 2, okay, then mod of x is not equal to x, okay, because mod of x will be 2 while x is minus 2. So, mod of x is not equal to x, and therefore, the truth value of this statement is f. Okay. So, for every x, p x has truth value f, okay. Truth value is f, okay. And then here second case, for every x, x plus 1 greater than x. If we take any x belonging to R, for any real number x belonging to R, then x plus 1 greater than x is always satisfied. Okay. So, this statement is always true. Okay. So, its value is true. So, its value is true. Okay. Now, let us take the third case. In this case, third, for every x, x minus 3 less than x. Okay. Now, take any x belonging to R, okay, then x minus 3 less than x is always true. Okay. So, its truth value is t. Okay. And then fourth case, for every x, x square equal to x. So, p x here is x square equal to x. Now, if we take x equal to say minus 2, let x be equal to minus 2, then x square is equal to x is not satisfied. Okay. X square equal to x is not satisfied, and therefore, truth value is f. Okay. So, x square for all x, p x is x square equal to x, the truth value is f. Now, let us discuss existential quantifiers. Let us consider these statements. Some people are students at St. Stephen's College. The second statement, there are some students at St. Stephen's College. Third is, there exists at least one student at St. Stephen's College. Now, notice that all these statements are equivalent in that they claim the existence of at least one object for which the predicate a student of St. Stephen's College is true. This symbol is used to denote there is, we can find, there exists, for some for at least one, Okay. So, in all these cases of objects for which a given predicate is true, we use this symbol. Okay. Now, we write there exists x belonging to s. This means there exists or for some or for at least one, okay, at least one and so on. So, this symbol, there exists x belonging to s such that p x, okay. We write like this, where s is the set of all people, p x is the is being a student in St. Stephen's College. Okay. So, this p x is denotes a student in St. Stephen's College, and this denotes a set of people. So, we can write the sentence these sentences, these statements, Okay. These statements in symbolically in the following form. If our S denotes the set of all people, then we can write those three statements in the form symbolically in the following form. There exists x belonging to x such that p x, where p x is the predicate a student in St. Stephen's College. Now, let us define existential statement. Okay. So, existential statement is a statement of the form there exists x belonging to D p x, or there exists x p x, or there exists comma D intersection p x. Here domain, you can see domain D is included in the expression. Okay. So, we do not if we do not write D here, then we include D in the predicate. We write instead of predicate p x, we write D intersection p x. So, here p x is a propositional function defined on the set D. Okay. D x p x is a propositional function defined on the set D. Hence, the truth set. Okay. The truth set, and now truth set is also defined as domain of discourse. Okay. So, it is not an empty set, because there always exists some x belonging to S for which p x is true. Okay. So, the truth set is not the empty set here, that is T p equal to x such that x belonging to D p x is true is not equal to phi. Okay. So, we can say the following, that T p is not equal to phi if and only if, this is if and only if T p is not equal to phi if and only if there exists x p x. Okay. So, there exists x p x is true and T p is equal to phi if and only if there exists x p x is false. Okay. Because if there does not exist any x belonging to S for which or D for which p x is true, then T p will be equal to phi. So, the truth set of p is equal to phi if and only if there exists x such that p x is false. Now, let us look at this statement. This statement, there exists n belonging to n plus 7 less than 6. Okay. You can see if you take any n is equal to 1 or 2 or 3, then n plus 7 less than 6 is always false. Okay. So, for no n belonging to n plus 7 less than 6 is true. Okay. Therefore, T p, okay, T p is equal to the set of all n belonging to n such that n plus 7 less than 6 is equal to phi. Okay. So, the truth value of this statement, okay, truth value of this statement is truth set of this statement, this is truth set. Truth set of this statement is empty. Let us take another example. The statement, there exists x belonging to R is the set of all real numbers. So, the statement, there exists x belonging to R, x square minus 1 equal to 0. Okay. This statement is true because T p is not equal to phi. Okay. T p is equal to the set containing minus 1 and 1, because for x equal to minus 1 and x equal to 1, x square minus 1 equal to 0 is satisfied. So, when T p is not equal to phi, we have seen here, when T p is not equal to phi, okay, the statement, existential statement, this is existential statement. The existential statement is true. So, let us say, let the set of real numbers R be the universal set. Okay. Then let us consider these statements, there exists x square equal to x. Now, here T p equal to set of all x belonging to R x square equal to x. This is equal to 0 and 1, okay, 0 and 1. So, it is true, okay. It is not phi. okay, it is not phi. Therefore, the truth value is t, and here in this case T p is equal to 2x equal to x means only x equal to 0 will satisfy this. So, this so T p will be equal to singleton set containing 0, and therefore, this is not equal to phi. So, again it is true, and then there exists x such that x square minus 2 x plus 5 equal to 0. Now, x square minus 2 x plus 5 equal to 0, if we consider this equation, then you can see discriminant here. Discriminant is equal to b square minus 4 a c. So, minus 2 whole square minus 4 into 5, that is equal to minus 16. Okay. So, discriminant is negative, and therefore, its roots are complex. Okay. So, for no real value of x, x square minus 2 x plus 5 equal to 0, and therefore, T p is equal to 5, T p equal to 5. So, truth value of this statement is f. Okay. And then there exists x such that x plus 2 equal to x. Now, for no x belonging to R, x plus 2 is equal to x. Okay. So, this here T p is equal to phi again. Okay. So, the truth value of this statement is f. With that, I would like to end my lecture. Thank you very much for your attention.